Okay, so what I'd like to have you do is jot these notes in your lab notebook. Pretty much what I would say you could do is leave a couple of pages if you're not done with your LD50 lab and put a new table of contents entry in called accuracy and precision, and then take these notes there. And I'll tell you if it's something that you should or shouldn't write down. So, at the end of this, you should be able to explain the difference between the accuracy and precision, um, and give examples of accuracy and precision. And we are going to be doing a measuring lab on Monday, and the measuring lab is going to relate to accuracy and precision. So it's all about measuring. When our lab on Monday will be tools of measuring, and the thing is that you should know, and I mean we've said the word measurement before, but it is a quantity that has both a number and a unit. And a lot of times our measurements will be recorded in scientific notation. And scientific notation is in the form of m times 10 to the n. M is equal to or greater than 1, and n is an integer. And let me add to that that not only is uh, it greater, or excuse me, not only is m equal to or greater than 1, but you could also add to that that it's less than 10. Okay, so it won't go over 9.99. An example would be 2.5 times 10 to the negative 2. If you have that negative 2 there like that, that just says that it's a small number. It's smaller than 1. We'll talk more about scientific notation later, but our main focus for this is accuracy and precision. So accuracy is the extent to which a measured value agrees with a standard value, a standard. So we have accuracy of devices. They must be checked when we get new balances from the supply companies. We have to check to make sure that they are accurate before we put them into use. And the way we do that is by taking a weight that is a specific accepted value, and we measure that weight on the balance and see if it indeed is that weight or mass. Um, One other thing, that example that I just gave you was for balances, but if you are reading a piece of equipment like glassware, like you have been for your LD50 lab and how you will next week, you need to be careful of something called parallax. And you don't have to write the definition of that, but this is what it means. You need to make sure that when you are reading a device, that you are not reading from above or below, because that will change the actual amount. It will not be accurate. You need to read at eye level, and if that means that you need to put your graduated cylinder on a table and then squat down to look at it at eye level, that's what you need to do. But you need to read at the bottom of the meniscus, and we'll look at some more examples of that momentarily. So if we look at these numbers, the question is, who is more accurate when measuring a book that has a true length of 17.0 centimeters? So if we look at these numbers and look at the average of them, you can see that the first measurements, Susan's work, these measurements are in the range from 15 to 18. Okay, so if you were to take the average of that, it would fall somewhere, maybe 16 point something or 17 point something. Um, Now, if you look at these numbers, Amy's numbers, none of them are even close to 17. So if you had to say which of the two is more accurate, hopefully you would choose Susan. Now, the way that we determine accuracy is by determining error. So, like I said, you have the accepted value or the standard value, and that is like the general agreed upon value in the scientific community. So, if I have a pre-measured weight and it is 500 grams, then that is the standard. And then you have your experimental value, which is a value that is measured during the experiment. So maybe we put a mass of sugar on a balance and it reaches 500 grams. That's our experimental mass. So the error would be experimental minus accepted. That's how you calculate the error. And you use the error to determine the percent error. And percent error is the absolute value of the error, okay, so that it's a positive number, divided by the accepted value multiplied by 100. So it ends up to be this formula. Percent error is equal to the absolute value of error divided by the accepted value multiplied by 100. So if you look at an example, you have a thermometer, let's say, that reads 99.1 degrees Celsius. Sorry. Hold on. Okay. And the accepted value is 100 degrees Celsius. The question is, what is the error? And then what is the percent error? So you're going to use these formulas. So first of all, the error is experimental value minus accepted value. And then your percent error is the error over the accepted value. So experimental value in this case would be the 99.1, and the accepted value is 100. And so experimental minus accepted, 99.1 minus 100. And then percent error, you're going to take that number and you're going to divide by accepted. And then multiply by 100. Now, I have this all on the next slide, so I don't know why I don't just take you over there. But experimental minus accepted. So again, in this case, this is experimental, this is accepted, this is accepted. A lot of times that is what people will mess up the most, is which is which. And here's a breakdown of the calculation of it. So 0.9% error is very good. You want the smallest percent error that you could possibly have. If you have 0% error, that means you were perfect. You're perfectly accurate. So to summarize, to calculate how accurate a measurement is, you use percent error, which is actual minus experimental divided by actual times 100. And I want to point out in this one, I have these switched, but because it's an absolute value, it doesn't matter. And for some reason, the absolute value isn't in this graphic. So precision is the other topic, and this is the degree of exactness of a measurement that is repeatedly recorded. So if we have these 3 sets, and you look at them, and the question is, which set is more precise? So which one has the smallest spread? And if you look at the numbers, the low number for the first one is 18.2, and the high number is 18.4. So the difference between the lowest and highest number is only 0.2. Now, if you look at this next set of numbers. Our low number is 17.9 and our high number is 18.85. So that is quite an increase. It's almost an increase of one. It's 0.9 something. And then if you look at the third set, you have 16.8 as the low number and 19.44 as the high number. That's even larger of a spread. So if we had to choose which one of these are the most precise, that would be 18.2, 18.4, and 18.35. My star does appear a little low, but it is meant for that first set of numbers. Here's more. Let's say that we are measuring the same 17.0 centimeter book that we measured when we were testing for accuracy. Now, the question here is Susan versus Amy, which one is more precise when measuring? So Susan has all these different numbers. She has 17, 16, 18, and 15, okay? Amy has all within a few tenths of each other, and they're all in the 15 range. They're not accurate, but they are precise because they are right around the same number, multiple readings. Now, to calculate how precise a set of number is, we use standard deviation. And a general definition of that is the average away from the average. And this is the formula for it. Don't worry about that right now. More later. So some examples here. So we have two bullseye, and we have arrows, and we have bullseye 1 and we have bullseye 2. And if we look at bullseye 1, is that accurate? Is that precise? It's very accurate because it's almost at the very middle. It's very precise. So high precision, high accuracy. Now, the second bullseye, they are not in the middle. Okay, so they're not accurate, but they are very precise because they're all around the same area. Okay, so now 3 arrows in each of these targets are coming in, and we are going to decide if they are accurate, precise, or not. So how do they compare? Well, the first one, obviously hitting the bullseye 3 times in a row, almost all on top of each other. So this first bullseye is both accurate and precise. Second bullseye is kind of like the second bullseye in the previous slide, where you have 3 that are very close together, but they're not at the bullseye. So it is precise, but not accurate. Third one, is it precise? Is it accurate? Neither. It is neither accurate nor precise. Now, can you define accuracy versus precision? Let's do this last example. This is one that I think you should draw so that you have another final example. So you need to evaluate whether the following are precise, accurate, or both. So press pause here and you make your best guess and then come back after and replay. Low accuracy, low precision. Low accuracy, high precision. High accuracy, high precision. Can you define accuracy versus precision?